So, being able to have batteries, being able to use devices that require them, we need redox reactions, and then the downside is the rusting or the corrosion that you see on any kind of metal, because metals are usually involved in these redox reactions. Although they don't have to have metals, but a lot of them involve metals and the transferring of electrons from metal to metal. Okay? So, first thing though is rules for assigning oxidation numbers. Okay? Generally, the atoms on the periodic table, the elements on the periodic table are going to follow their normal charges, except for a few in certain cases. So, like the alkali metals that are in group 1, what is their charge going to be? What charge do the alkali metals go to?
Plus 1.
Plus 1, always. How about the alkaline earth metals in group 2?
Plus 2.
Plus 2. How about the aluminum group, boron group over here?
Plus 3.
Plus 3. Then the carbon group is going to be
Plus 4.
plus or minus 4. Then nitrogen group,
Negative 3.
negative 3. Oxygen,
Negative 2.
negative 2. And
Negative 1.
negative 1 for the halogens. And 0 for the noble gases, although the noble gases don't play a role because they don't react. What you do need to remember too is a few of the others, like our non-mogs, like zinc and silver. What are zinc and silver's charges? Zinc is plus 2, silver's plus 1. Follow the diagonal. Aluminum plus 3, zinc plus 2, silver plus 1. Okay? Now, these guys over here that do the anions, nitrogen group, oxygen group, and chlorine group, they follow their normal charge when they are in the anion position or the second part of the compound. If they're in the first part of the compound or the middle part of the compound, they're not going to follow those normal assigned charges. Okay, just so you know. We're going to do a couple examples like that. But the metals typically follow their normal pattern of charges. Okay? Another thing to note is anything in its elemental state, anything that's a free element, like chlorine, any of your diatomics, any element written by itself, like zinc or aluminum or H2 or F2, anything like that where it's by itself in its elemental state. You might even see weird ones that look like this, where you have this P4. That's actually phosphorus, elemental phosphorus, or S8. You see something like that, that is still just elemental sulfur. Okay? All of these get assigned a charge of 0 because they are considered neutral. So anytime you have an element by itself and the diatomics count, so Brinkelhoff counts, hydrogen, nitrogen, oxygen, chlorine, bromine, iodine, they all count in that the category of getting zeros. Okay? The next thing that you have to realize is that the monatomic ones usually follow their charges, like I just showed you, like the alkali metals go to plus 1, alkaline earth metals go to plus 2. Your moms, like iron, you have to look at the compound to figure out their charge, just like you used to in ionic compounds. Okay? Hydrogen is a little bit of a tricky one. Hydrogen. Hydrogen is usually plus 1, and that's when it's with non-metals. If hydrogen is with a non-metal, it's going to be a plus 1. Okay? If you see hydrogen with a metal hydrides, that's when they go to minus 1. So when hydrogen is with a metal, you'll see it'll be a minus 1 charge, or minus 1 oxidation number. Now, oxidation number of oxygen for our purposes is always going to be a minus 2. The exceptions are the peroxides, but we're not going to do peroxides in here. That's more of an AT thing, so we won't do peroxides in here. So when you're looking at oxygen, just automatically assign oxygen as a minus 2. For a neutral compound, the sum of the oxidation numbers should add up to 0. Just like a regular ionic compound adds up to 0. So in KNO3, potassium nitrate, the K gets a plus 1, the oxygen gets a minus 2, and in this particular case, the nitrogen doesn't follow its normal charge because it's not in the last part of the compound, it's in the middle part of the compound. See how it's in the middle here? Okay? When it's in the middle like that, you have to calculate its charge. So it's not going to do the -3 thing here. Okay? So in this case, the nitrogen ends up being a +5. If you have a polyatomic where it has a charge on it, like SO4, SO4 has a -2 charge, then you need to total it up to -2, not 0. So when you figure stuff out, you need to add it all up to -2. So in this case, SO4, if oxygen is -2 and there's 4 of them, this means this is a -8. The whole sum should equal -2. So what is sulfur's charge going to be then? Something plus -8 gives you -2. So in that case, sulfur is a +6. Okay? So that's how you would kind of work that one out there. You can kind of set up these mini algebraic expressions to figure it out. And we're going to do some together right now. Okay? So let's do some together right now. So, number 1, silver oxide. What's oxygen's charge always? Oxygen's charge is always a -2. So what I do is I just put it up here so I can figure everything out. Now, that means this side of the molecule is worth a -2. Or this side of the, this is a formula unit because it's ionic compound. Now, that means the silver side also needs to add up to +2 so that we can equal 0, right? We need that 0 amount. So if we have 2 silvers and we need a +2 out of those 2 silvers, how much is each worth? Each one's worth a +1. So silver's charge, silver's oxidation number is a +1, oxygen's is a -2. Let's look at number 2. I'll erase this. All right. Once again, copper with chlorine here. As you see, chlorine is in the second position. It is the anion here. So it's going to follow its normal charge off the table. What's chlorine's charge off the table? The halogen charge. It's a -1. Good. So -1. There's 2 of them, so this side totals up to how much? -2. So in that case, the copper has to add up to +2, and there's only 1 of them. So the copper has to be a +2. Because +2 minus 2 equals 0. So this has to be a +2. Cl -1. Now for number 3 is an interesting one. Does anybody notice anything interesting about number 3? What kind of compound is number 3? A what? What kind of compound is P2O5?
I think it's ionic.
Is it ionic? Is there a metal there?
No, so I think it's covalent.
It must be covalent. Good. And covalent compounds, what do they do with their electrons? Are they transferring them or sharing them? They're sharing them. Okay, so it seems kind of interesting that we would be assigning charges to something in a covalent compound molecule here. Now, they're not really transferring in and of the molecule itself, but we assign oxidation numbers for covalent compounds just to keep track of where the electrons might go during a reaction. So I'm still going to give them charge numbers, some oxidation values, without them really, they're not transferring electrons, and it's not an ionic compound here, but I'm assigning them a value so that when it does a reaction, I know if the charges do change, and I know if there's any transfer of electrons going on during the reaction. So in that case, oxygen's always going to be a what? -2. So I can figure that one out easily. So this is a -2. How many of them are there? So this totals up to -10. So that means this side has to be a +10. So if there's 2 P's, and it has to add up to +10, how much is each P worth? Each P must be worth a plus 5 because there's 2 times the plus 5 gives you plus 10, right? And this has to total up to 0. So the P is a plus 5, the O is a minus 2. Anybody know what number 4 is? What's PO3 minus 3? It's not phosphate, it's close though, because PO4 minus 3 is phosphate. This one's phosphite. Okay, so that wasn't one you had to memorize. I was just checking to see if you knew it. In this case, it needs to add up to what? -3. Very good. We need to total it up to the charge value here. So, when I work it out, I'm going to erase this up here so that I have more room. All right, so oxygen is always what? -2. How many of them are there? 3, so 2 times 3 gives me a -6. Remember, this has to equal -3, has to total up to -3 here. So, something plus the -6 gives us -3. What's that P got to be? P has to equal a +3, and O, of course, is still equaling that -2. Good. Now let's do like number 1, where we have 3 elements in the compound. This is potassium chlorate. Oxygen's always a what? What's oxygen? -2. Okay? So this is -6 out of the oxygen side. Now, like I said before, chlorine is not the last element in the compound, so it's not going to do the -1 here. But the other element I do know is potassium, because potassium only goes to 1 charge. What charge is potassium? What's its oxidation number always going to be? +1, because it's an alkali metal, right? So this is +1. So something in the middle here has to make it add up to 0. So what is the chlorine's oxidation number going to be in this particular instance? Cl has to be a +5. Because +5, +1, -6, that all adds up to 0. So, like I said before, those anions, the nitrogen group, oxygen group, the chlorine, the halogens, they don't always follow that normal charge system. They only follow the normal charge system if they're the second part of the compound, the last element in the compound. So, let's look at number 2 then. PCl3, another covalent compound. But where is the Cl this time? Is it in the middle? Is it in the front? No, it's on the very end. So what do we do with it? If it's the second part, we assign it its normal charge. What's its normal charge? -1. Good. So this means this side is a -3. So that means the P has to be a +3, right? To equal 0. So P equals a +3. And let's do number 3, and then I will have you do 4, 5, 6, and 7, and 8 on your own for practice. Number 3 is called arsenate. It's another one of those polyatomics that you don't have to memorize, but it actually exists in nature. Whose charge do I know off the top of my head? Oxygen, because it's always a -2, right? Oxygen's always -2. How many of them are there? 4, so this represents a -8. Remember, we have to make this add up to -3 because it has a charge on it. So in this case, if there's only one arsenic, what does its value have to be? What is AS going to be? So AS equals +5. Now you try a few on your own. Okay, so check these, see if you got them. For sulfur hexachloride, the S has got to be a what? What'd you get? +6 is correct. Because the chlorines are in the anion position, they would follow the -1 charge. So the sulfur has to be a +6. How about for aluminum phosphate? What charge is on the oxygen? Oxygen's always a what? -2. And the aluminum, it only has one fixed charge. What's its charge? What's aluminum? +3. So if this 2 times, the -2 times 4 gives us -8. This one's a +3. What does our phosphorus have to be in order to equal 0? Phosphorus has to be a +5 in this case. How about 6? Carbon is the what? +4. Chromate. This one needs to equal a -2, right? Oxygen's -2, that's a -8. So something -8 is going to give you -2. So that's going to be a +6 for your chromium. And last but not least, silicon dioxide, -2. So that's going to be a -4. So silicon has to be a +4. Signing oxidation numbers. Good. Now let's look at half reactions. Half reactions. And a little bit of some definitions. Redox is short for oxidation and reduction, or reduction and oxidation. Redox is a short way to say both together. It is a partnership, by the way. 2 players involved. And it is an exchange of electrons, a transferring of electrons. One element has to lose electrons in order for another element to gain electrons. So it is a nice little partnership. You can't have one without the other. Now the way I remember it is I use the oil rig system. Oxidation is loss, and I mean losing electrons. Reduction is gain, and I mean gaining electrons. Okay? You could also use the Leo Gur one. Some people like that one better, like Leo the Lion says Gur, I guess. I don't know. So losing electrons is oxidation, so Leo, and gaining electrons is reduction. Okay? Either way, it's a good system of how to remember which way the charge is going to flow. If I lose electrons, electrons are negatively charged particles. Guess what? I'm going to become more positive. So my charge value should increase and become more positive if I'm being oxidized. If my charge is becoming more negative, that means I'm gaining those negative little electrons. So therefore, I'm being reduced. And we use half reactions to represent represent the exchange of electrons. So it's only showing you one part of the element that's either gaining or losing. In this case, we have fluorine with 0 charge, and it is gaining an electron. Okay? It's going from 0 to -1. Am I becoming more positive or more negative? 0 to -1? Negative. And becoming more negative, gaining electrons means I'm being reduced. Okay? Now, if we look at the other example here, I have sodium plus. I kind of covered up the plus, but this is a +1 here. And it is going to 0, right? Oh, that's not right. This should be, if it's giving away an electron, this should be a +2, by the way. Change that. That should be a +2. Not a 0. It should be a +2. The sodium has lost an electron. Okay? Went from +1 to +2. An electron is being given off as a product. Okay? It's becoming more positive. +1 to +2. You're more positive. There you go. That is when you're being oxidized. And they put the oil there. Example of oxidation. So if you're looking at your examples down here, and they get pretty easy too, because if electrons are a reactant, you're being reduced. If electrons are a product, you're giving them away, you're being oxidized. So you could look at it that way. I always look at the charges though. Compare the charges, before and after. My charge before is a 0. My charge after is a +2. Am I being oxidized or reduced? Oxidized, because I'm becoming more positive. So this is the oxidation. Looking here, starting at +2, going to +3. Am I becoming more positive or more negative? Becoming more positive, I'm being oxidized. Okay? Oh, the next example here. I'm going from 0 to -2. Am I becoming more positive or more negative? More negative. In this case, I'm being reduced. Yes. So this one would be reduction. Kind of get the idea? So I'd like you to go ahead and do those. So quick check here. Make sure you got these. This one is oxidation because we're going from -1 to 0, becoming more positive. +2 to +1, that's being reduced. You're becoming more negative. +1 to 0, becoming more negative. 0 to -1, reducing again, becoming more negative. +2 to +4, that's oxidation, becoming more positive. +2 to 0, reduction, becoming more negative. +4 to +2, that's reduction. And +4 to -4. Wow, is that a huge reduction? That's 8 electrons being transferred. +3 to +2, that's only 1 electron. So that one is also reduction. Lots of reductions. Now it's going to get a little bit more complicated, hopefully not too much. So let's take a look down here where we have an actual reaction. Okay? So, when you have an actual reaction, you're going to want to first make sure it's balanced. Okay, we see a coefficient of 2 here. It's balanced. Good. Now, the next thing you want to do above each element is assign the charges, as you see that they've already done. Zinc is by itself, so it gets a 0. Hydrogen's by itself, so it gets a 0, because those are elemental forms. They're neutral, so they get 0 charge. Then you look to the compounds to assign them. In this case, the hydrogen is with a non-metal, so the hydrogen gets the +1, and the chlorine gets the -1. Zinc, remember, is always +2. We know that one from our memorizing. And then the chlorine goes to -1 because it's the anion position of that compound. Once I have all the charges in place, I can start identifying which species is which. So if I'm looking here, zinc is going from 0 to +2. So is zinc being oxidized or reduced? So zinc is the one being oxidized. Now if I'm looking here, I have hydrogen and I have chlorine. The chlorines, though, guess what? They're staying the same, so they're not really participating in the redox reaction. Okay? But if we look at the hydrogen is a +1 going to 0. So +1 going to 0 is being what? Reduced. So we put the H here. Now, we need to identify our agents. We have a reducing agent, and we have an oxidizing agent. Now, this is how the agents work. It's going to sound a little backwards, but please pay attention. Here, zinc is being oxidized. Zinc is giving away electrons, right? But zinc is actually the one causing hydrogen to be reduced. Does that make sense? Because it's making the hydrogen take those electrons. So, in essence, zinc is going to be the reducing agent because it's making the reduction happen. Everybody see that? And so if you're being oxidized, you are the reducing agent. Okay? So the reducing agent here is going to be zinc. And vice versa works here too. If you're being reduced, like hydrogen is taking electrons in, that means the hydrogen is causing the zinc to be oxidized. And if you're causing the oxidation, you are called the oxidizing agent. So it's opposite, but in this case, the hydrogen is going to be the oxidizing agent. Okay? So let's do a few examples on the next page. And make sure we're following our instructions here. First, balance. Then write the oxidation numbers for each element or polyatomic group. If you have polyatomics on both sides, you can keep them together, which is nice, and you don't have to do them individually if they're on both sides. So, and then we're going to figure out which one's which and then do the type of reaction again. That's just a good little review anyways. So, looking at our first one up here, let's check and see if we're balanced. 1 zinc, 1 zinc. 2 hydrogens, 2 hydrogens. 1 sulfate, 1 sulfate. Are we balanced? Good, nice and balanced. Now I'm going to assign charges, assign oxidation numbers. Easy ones. 0, 0. Why would I put zeros on them? They're by themselves. They're just in their elemental form, so they are neutral. They get zeros. Now for the harder part. What is sulfate's normal charge? Instead of breaking up the S and O here, let's just do the whole sulfate together. It's a -2, right? So the sulfates aren't changing. So the sulfates really are like spectators in the reaction. They're watching the show, but they're not participating, okay? But the zinc and the hydrogen, in this case, our hydrogen, what is its value going to be? If sulfate's a -2 and there's 2 hydrogens, each hydrogen has to be a +1 because there's 2 of them, so they add up to +2. But each individual one is a +1, right? Zinc is always a what? We know this one. +2, right? Now that we've identified our charges, we can figure out who's being oxidized and who's being reduced based off of the oxidation numbers. Zinc is going from 0 to +2. So zinc is becoming more positive,
It's going to be oxidized.
oxidized. So therefore, zinc is also the reducing agent. Good. So you can kind of do those two together. And if we look here, we know the sulfates are not participating. If we look at our hydrogen, hydrogen is going from +1 to 0, becoming more negative, which makes sense because we need something being reduced here. So hydrogen's being reduced, and it is therefore the oxidizing agent. Now, what type of reaction is this? Remember those types of reactions like decomp, synthesis, that kind of stuff? What kind is this one? It is a single replacement. Good. Single replacement. Remember, we have one switch going on. The zinc switches with the hydrogen. Okay, so it's single replacement. Let's do the next one. The next one's a little tricky, so I'm going to help you out with it. Because if you look here, what do we have on our reactant side? We have water. But here we have H's and we have OH's. What do we do when we have that kind of combo going on? What do we do to our water? Make our water a what? HOH. We're going to change the water to HOH here. Because I have an H group and I have an OH group. Now I need a balance, so let's balance. Who's out of balance? H is out of balance. We have 2 right here, but only 1 right here, so I'm going to put 2 there. What did I throw out of balance by doing that? So OH, the hydroxide, so I'm going to put a 2 here to fix them. And last but not least, I've thrown my sodiums now out of balance, so I'm going to fix them and put a 2 here. So now that we're in balance, we can keep moving. So we're going to start assigning our oxidation numbers. Who gets the zeros? H2 and Na, right? Both are 3 elements by themselves. Now, looking at here, we have hydroxide on both sides, so I'm just going to give them both their -1s. Okay, the hydroxides aren't really changing. And let's look at our H here. H is going to be a +1. The sodium's going to be a what? Sodium's an alkali metal, so it's going to be a +1. Good. Now that I've assigned everything, I can look for my changes. Sodium goes from 0 to +1, so sodium being oxidized or reduced. 0 to +1. Oxidized, good. So it's the reducing agent. We look here, our hydrogen going from +1 to 0. +1 to 0 means hydrogen is being reduced. Good. And therefore, the hydrogen is going to be the oxidizing agent. Now, this one's a little tricky too. What kind of reaction is this one? The Na switches with the H. So kind of a hard one to see. It's single replacement. Okay, single replacement. One other thing to note on the organic combustion that's next, the hydrogen is with the non-metal, so that it's going to be a +1. That means the C's got to be a -4, just so you know. Okay? So, finish this up. Study for your quiz. On Friday, check Blackboard if needed. Watch YouTube. One other quick thing is that you need to realize that some of our reactions, there's one specific type that's not going to change its charges, so it's not a redox. So when you're looking up here, and if none of the charges change, you can write in the boxes, it's not a redox. Okay, and there's one specific type of reaction where that's going to occur.